Now we're going to take a look at the types of conformations that cyclohexane can adopt. So we've been drawing cyclohexane like this, but we need to talk about this kind of representation a little bit. First of all, if we're looking at the model on the left, you could say that there's a top of the ring and a bottom of the ring. And we would say that the atoms that are red are sticking up out of the top of the ring. And we could draw those in on the structure over here as red solid dashes to indicate that they're coming out of the plane of the board or the screen. So this would mean that we're sort of looking down on top of this ring from this angle. On the other hand, on the bottom of the ring, you have these white atoms, and so we're going to indicate that they're going into the screen with dashed wedges. And so again, this would be looking down. You would see those going away from you. But there's a couple of problems with thinking of cyclohexane like this in 3 dimensions. One is that the angle strain here, it has to deviate from 109.5, which is the ideal geometry for a tetrahedron, the ideal bond angle. And it's strained a bit. It's having to pull away from that to be able to lie flat. The other problem is if you were to look down each one of these carbon-carbon bonds, you would see that there's a lot of eclipsing taking place, so the torsional strain is maximized here. And if you had any groups on here besides hydrogen, you would also see steric strain introduced as well. So in reality, cyclohexane will not lie in a flat ring like this. What it actually does is it puckers up into this so-called chair conformation. And it's called a chair because it kind of has this shape like a chair. If you were drawing this on a piece of paper, you would represent it this way. And I would show the white hydrogens out like this. This one here, down here, here, and I'm going to show that one sticking out of the bottom and the back. The red atoms, I would show here, 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 and like this. That takes some practice of getting used to, number one, drawing that shape, and number two, being able to relate the drawing here with the structure there and telling what everything is. So I'm going to go ahead and label these carbons just arbitrarily. I'm going to number them. Let's try 1, 2, 3, 4, 5, and 6. And then I'm going to show you the way I have that represented here. 1, 2, 3, 4, 5, and 6. If you're having a little trouble with that right now, don't worry, that's perfectly normal to not see this right away. You might want to pause the video and take a couple of minutes to take a look at the numbering and the way that we have depicted this structure in 3 dimensions. The reason that it adopts this shape is because it relieves the angle strain, and it's also going to relieve eclipsing. So this is the lowest energy conformation for a 6-membered ring.